in 6.5, I want to start out and do a slight or a quick review on what we talked about at the end of 6.4. We looked at the difference between a population distribution and a sampling distribution. And I just want to remind you that a population is a set of X values. Each one represents an individual value. Sampling distribution is a whole set of X bar values, which it means each number refers back to the average of a sample. And we looked at mu and sigma, and then mu of X bar and sigma of X bar. So we talked about this just a little bit. So we want to go further with this. It says for a normal probability distribution, let X be a random variable with a normal distribution whose mean is mu and whose standard deviation is sigma. That's talking about this right here. Let X bar be the sample mean corresponding to random samples of size n taken from the X distribution. So that would be your set of X bar values. Then the following are true. The X bar distribution is a normal distribution. Here's what that is saying. If you know this is a normal distribution, then automatically this is a normal distribution as well. And just as a reminder, that is important because in order to be a normal distribution, it allows you to use the Z table. The mean of the X bar distribution is mu. Here's what that is saying right here. Mu from the population distribution is equal to mu of X bar. So what that is saying is these two values are equivalent. So again, we're kind of talking about those numbers being ages. So if you knew the average age of mu, this number calculated to be 20, then you know this number would be 20 as well. They're equivalent, they are the same. Now, the standard deviation is not the same. The standard deviation of the X bar distribution is sigma over the square root of n. So what that is saying is the standard deviation of the sampling distribution is not equal to sigma, but to sigma divided by the square root of n. So you need to be familiar with these. Now, these formulas are down here as well. Okay, this talks about how to convert the X bar distribution to the standard normal Z distribution. So we have already talked about how the mean of the sample distribution is equal to the mean of the population distribution, and that the standard deviation of the sampling distribution is equal to sigma over the square root of n. N is the sample size, mu is the mean of the X distribution, sigma is the standard deviation of the X distribution. Now, the part that is of most significance to us is this right here. And that is how to standardize your value. And to standardize your value, then we will take X bar minus mu divided by sigma divided by the square root of n. So this says if you're given X bar, you will use this formula to change it to a Z, which means you are standardizing the value. Now here's the main thing you need to remember. If you're talking about X values, meaning one person or one item, then to standardize that, we're going to use X minus mu divided by sigma. But if we are talking about X bar values, meaning the average of several people or several items, then to standardize that value, you take X bar minus mu divided by sigma divided by the square root of n. So when you're converting, you're going to be using one of these two formulas. So you need to always ask yourself, is the problem talking about one person, one item? Then we standardize our number using this formula. Is the problem talking about the average of several people or several items? Then we use this formula here. So that's what we're going to be doing then, is several examples to get you familiar with recognizing this. The manufacturer of a new compact car claims the miles per gallon for the gas consumption are normally distributed with mu of 25.9 miles per gallon and a standard deviation of 9.5. 30 cars are tested. Okay, well, they give me mu, 25.9. They give me sigma, 9.5. And when it says 30 cars are tested, that means they drew a sample of 30 and they're going to test those 30 cars. So that 30 is N. So then, if you'll look here, we have a probability. Now, this is familiar and kind of looks a lot like what we've done. But what you really need to recognize is that this is an X bar instead of an X. Now, as far as calculating the probability and using the table, it's the same. When I see less than, then I know once I have my standardized value, I just go to the table and use that number. But because it's X bar, then I know which Z formula to use. So it would be X bar, 23, minus mu, 25.9, divided by sigma, 9.5, divided by the square root of N, which is 30. Now, here's where you need to put your parentheses. You enclose the numerator and the denominator. So I'm going to do this on two different calculators so you can see this. So I would do open parentheses, 23 minus 25.9, close parentheses, divided by open parentheses, 9.5, divided by the square root of 30, and then I right arrow over to get out from under that radical, and then I close parenthesis. And Z values, 2 decimal places, normal rounding rules, negative 1.67. Now, if you have this calculator, it's slightly different, but not a lot. I would do open parentheses, 23 minus 25.9, close parentheses, divided by open parentheses, 9.5, divided by the square root of. Now, this calculator, when you open a square root, it puts that, what's under the radical, in parentheses. So I'll put 30 in the parentheses and close it, and then I'm going to close my denominator, and you'll get the same answer. So now I have my standardized value. I'm going to go to the table and locate that number, and since it's a less than, then I just use the number from the table. So negative 1.67. So negative 1.67.0475. So this equals 0.0475. All right, now I have two values, and notice again this is an X bar. So it is between 23 and 28. Now this first one, when I standardize 23, we already standardized 23. That's negative 1.67. Now I need to standardize 28, so that would be 28 minus 25.9 divided by 9.5 divided by the square root of 30. And when you put that into your calculator, you should get 1.21. Calculate it real quick just to make sure. 28 minus 25.9 divided by 9.5 divided by the square root of 30, 1.21. All right, now when it's in between, if you recall, we need to find both areas to the left of these two Z values. Well, we already found this one. It was 0.475. And now I'm going to look at my table at 1.21. Well, there's 1.20, 1.21, so it's 0.8869. And then when it's between, if you remember correctly, we subtract these two numbers, and it's always the larger number minus the smaller number. And when you subtract that, you get 0.8394. All right, next example. A team of biologists has been studying the Pinedale Children's Fishing Pond. Let X represent the length of a single trout taken at random from the pond. This group of biologists has determined that X has a normal distribution. So what that tells me is, as long as it's normally distributed, I do not have to worry about my sample size, with a mean of 10.2 and a standard deviation of 1.4. So we know mu is 10.2 and sigma is 1.4. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches? All right, here's some things that you need to definitely pay attention to. What is the probability that a single trout, that means one fish, this is an X value. That is so important to recognize, because now when I find what is the probability that it is between 8 and 12 inches, this is an X value. Well, that is important, because when we deal with X values, we use this Z formula. So when we go to calculate or standardize our values, we have 8 minus 10.2 divided by 1.4. And we have 12 minus 10.2 divided by 1.4. You have to know which Z formula to use. So this gives me negative 1.57, and this gives me 1.29. So just like the previous example we did, since it's between two values, then I'm going to locate those two areas, negative 1.57, negative 1.5, and I find 0.07 at the top, 0.0582, and then 1.29, oops, 0.9015. And we're going to subtract those two, so 0.9015 minus 0.0582, and that equals 0.8433. And then the second part to this says, what is the probability that the mean length of 5 trout taken at random is between 8 and 5 inches? So the mean length of 5, so here we're talking about X bar values. So we're still doing the probability between 8 and 12, but the huge difference is now this is an X bar value. And where that makes a huge difference is in our calculation or our standardizing of the number. So now this is 8 minus 10.2 divided by 1.4 divided by the square root of 5. And here we have 12 minus 10.2 divided by 1.4 divided by the square root of 5. So when you plug those into your calculator, you're going to get, or you should get, negative 3.51 and 2.87. And we're going to go to the table. So we're going to look at negative 3.51. And when I go, well, I have negative 3.49, but I don't have negative 3.51. So recall, look at the very small print at the bottom, which says if it is a number less than negative 3.49, which negative 3.51 is, use 0 to approximate the area. So here, we just use 0. And now I look up 2.87. So 2.8, and then at the top I'm going to locate 0.07, and it's 0.9979. And then we're going to subtract those, which is 0.9979 minus 0. And of course that just equals 0.9979. So the big thing on this is you need to watch for a single trout, the mean of 5 trout, because it dictates which Z formula to use. Now, in both of these examples, we were told that the X distribution is normal. It said normally distributed, normally distributed. So we could automatically assume normal distribution for the sampling distribution as well. So what do we do if it doesn't tell us that? Well, we are going to look at what is called, or what is known as, the central limit theorem. So what if the X distribution is not known to be normal? Well, the central limit theorem states that if X possesses any distribution with a mean of mu and a standard deviation of sigma, then the sample mean X bar will have a distribution that approaches the distribution of a normal random variable. So it approaches normal with a mean of mu and a standard deviation of sigma over the square root of n, as n increases without limit, which just means as n gets bigger and bigger, you are approaching a normal distribution, which what I've said is just basically restated here, which means that X can have any distribution, but as the sample size gets larger and larger, the X bar distribution will approach a normal distribution. So that's what I just stated above. But how large is large enough to assume normal based upon the central limit theorem? The central limit theorem states that when n is sufficiently large enough, and it considers large enough being a sample size of 30 or larger, then normal distribution can be assumed. So basically what I'm saying, well, let's talk about that. It's basically what I'm saying is written right here. So to change X bar to Z, one of the following must be true. So this is what you have to watch out for right here. Either they have to tell you that the X distribution is normally distributed. If they do not tell me this, I can still assume normal distribution on the X bar distribution as long as n is 30 or larger. All right, so let's take that information and look at these. Suppose X has a normal distribution with a mean of 18 and a standard deviation of 13. If you draw a random sample of size 5 from the X distribution and X bar represents the sample mean, what can you say about the X bar distribution? It's just saying, can you say it's normal or not? And how can you standardize the X bar distribution? Okay, let's pull some stuff out here. They tell me that mu is equal to 18, sigma is equal to 13, and my random samples are of size 5. Now, 5 is not big enough in and of itself, but because they told me the X has a normal distribution, then when it says, what can you say about the X bar distribution? Well, the X bar distribution is normal because the X distribution is normal. So if it is normal, how can you standardize that? Standardizing means calculate the z-value, which is X bar minus mu, which they gave me as 18, divided by sigma, divided by the square root of n. So I've plugged in all the numbers given, but of course they didn't give me X bar, so we can't actually calculate it, but that's what it would look like in the formula. All right, so now, suppose you know the X distribution has a mean of 75 and standard deviation of 12, but you have no information to whether or not the X distribution is normal. If you draw samples of size 30 from the X distribution and X bar represents the sample mean, what can you say about the X bar distribution? Well, I don't know if X is normal or not. But in this case, that does not matter because this is 30 or larger. So I can say the X bar distribution is normal because the sample size is 30 or larger. How could you standardize the X bar distribution? So again, that would be X bar minus mu, which is 75, divided by sigma, divided by the square root of n. So it would look like that. And then lastly on this page, suppose you do not know that X had a normal distribution. Would you be justified in saying that the X bar distribution is approximately normal if the sample size were n equals 8? And the answer to that would be no, because the sample size is too small. All right, so let's look at some examples that apply the central limit theorem. Response time for a fire department is mound-shaped with mu of equal to 8.8 minutes and sigma of 2.1. So mu equals 8.8, sigma equals 2.1. A random sample of 32 response times is taken. So n equals 32. All right, when I look down here, I see that it's asking me to calculate X bar. So I need to ask myself two questions. One, does it tell me it's normally distributed? Well, when I read this, nowhere do I see normal distribution. But it kind of was a tricky way. It said mound-shaped. And if you recall, mound-shaped means symmetrical, which means that it's a normal distribution. You won't see it done this way very often. It will normally say normal distribution or it's normally distributed, but I wanted to point that out. But let's say it did not say this. Can I still assume normal distribution for the X bar? Well, in this case I can because my n is greater than 30. It just has to be equal to 30 or larger, and since it's larger than 30, so I'm covered both ways here. So since this is an X bar, when we standardize our Z value, it's going to be X bar 9 minus mu 8.8 divided by sigma 2.1 divided by the square root of n 32. So that plugged into your calculator gives you 0.54. Normal rounding rules to 2 decimal places. So now I need to go to my table. Well, I go, okay, this is a less than, so all I have to do is go to the table and use the number from the table. So 0.54 would be 0.7054. Now, this next example, it flips your variable and your number. So you have to be careful on this because you have to recognize that the mouth is open to the variable. So if I rewrote this, it would be x bar is less than 8 because you still have this, it's pointing to the, whoops, that would not be right. Sorry about that. X bar is greater than 8 is what I meant to put. So the mouth is open to the x bar and the inequality is pointing at the 8. Now, why you have to be careful on this is because as soon as you see this less than, students a lot of times will go, oh, I just used the number from the table. And in all actuality, this is a greater than, so you're going to do 1 minus the number from the table. But before I can find the number from the table, I have to standardize this value. And since this is x bar, to standardize that, that would be 8 minus 8.8 divided by 2.1 divided by the square root of 32, and all my parentheses, go to my calculator, and that is negative 2.15. So we're going to locate negative 2.15.0158. So it's 1 minus 0.0158, which is 0.9842. X is normally distributed with mu equal to 18, mu equal to 14, sigma equal to 3.4, n is equal to 10. So when I look here, I go, ooh, that's not 30 or larger, so that's too small, which is true, but because it says that the x is normally distributed, then I can assume normal distribution with this as well. So we're okay here as well. Notice this is x bar, so it would be 13.2 minus 14 divided by 3.4 divided by the square root of 10. Put all of that into your calculator, and you get negative 0.74. And you go to your table, and since it's a less than, you just use the number from the table, negative 0.701234.2296. Now, the next one you need to be very careful because look, this is now an x value instead of an x bar. So it's still a less than, and we're still using 13.2, but we're not going to get the same answer because now I use the different z formula. It would be x, 13.2, minus mu, 14, divided by sigma, 3.4. Plug that into your calculator and you get negative 0.24. It's still a less than. So negative 0.201234.4052. So now we're going to look at a problem like you might encounter that you have to be able to distinguish which z formula you're going to use. Suppose it is known the time spent by customers in a McBurger's fast food restaurant is normally distributed. So what that tells me is if I'm dealing with a sampling distribution X bar, I do not have to worry about how large the sample size is, because I can already assume normal distribution. With a mean of 24 minutes and a standard deviation of 6 minutes. So we have mu is equal to 24, sigma is equal to 6. Find the probability an individual customer will spend more than 25 minutes in the restaurant. So the probability more than 25 minutes. But here's what you need to be careful of. This says an individual customer, meaning one customer, so this is an X value. So this would be X, which means then when I standardize my number, I would use 25 minus 24 divided by 6. And that's 0.16666 or 0.17. Now, since this is a greater than, we have to do 1 minus the number from the table. So 0.17, 0.17, 0.5675, which gives me 0.4325. Part B, find the probability a random sample of 36 customers will have a mean more than 25 minutes. So here we're still doing probability more than 25 minutes, but you have to recognize that it says we have a random sample of 36 customers. So that tells me we're talking about X bar values. So now we're talking about X bar. Well, then that changes the Z formula that I use. So now it's 25 minus 24 divided by 6 divided by the square root of 36. And when you calculate that, it is 1. Now again, this is a greater than, so we'll do 1 minus the number from the table, and the number from the table, we're going to look for 1.00. So 1.00, 0.8413. And we get 0.1587. And that completes chapter 6.